Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will be the sixth to cover section 4.1 for Intro to Statistics, considering examining quantitative data. This video will specifically cover the four primary measures of variability discussed up to this point, as well as their advantages and disadvantages. The range is the simplest measure of variability to compute, as it requires only the maximum value and the minimum value in the dataset. For example, if we have the simple dataset of 3, 5, 2, 4, and 1, we have a maximum value of 5 and a minimum value of 1, the difference of which results in a range of 4. As stated, this is very easy to compute, which is really its only positive. On the downside, it ignores most of the data, as even in this simple example, 3 of the 5 values, or 60% of the data, were ignored, which becomes worse for larger and more realistic datasets. Furthermore, it is entirely dependent on extreme values, which makes it not resistant. Because it is not resistant, it tends to only be applicable for symmetric data, though we tend to instead use the standard deviation for symmetric data. The standard deviation, by contrast, is far more complicated to determine, and is the square root of the average squared deviations. When I say squared deviations, I am talking about the difference of each value and the dataset mean squared. Note that when calculating, the sample standard deviation divides by n minus 1 instead of just n, which means that it will always be larger than the population standard deviation, and tends to be considered an overestimation of the population standard deviation. As for advantages, it is a measure that comes with good interpretation and inherent meaning, particularly when talking about the normal distribution. It is also measured in the same units as the original data, which some measures are not, and it also uses all of the data. That tends to be a good thing, but it also comes with a weakness that it would also include outliers or extreme values, and thus is not resistant. Furthermore, when talking about the sample standard deviation S, it is a biased estimate of the population standard deviation sigma, since it is always a little bit off compared to its population equivalent. We also have variance, which is the squared standard deviation, or basically the standard deviation formula without the square root. In direct comparison to the standard deviation, this value is unbiased, because it is the sample variance that is trying to target or estimate the population variance. When we convert that into another measure, the standard deviation, bias is introduced that makes it less reliable as an estimator. However, it has more downsides. Namely, it has no interpretation and doesn't translate well as a visual measure of spread in data like the standard deviation or even the range does. And it also uses squared units of measurement. This is a problem as, if we are talking about values in feet, which is a length measurement, the variance thus would be a value in feet squared, which is an area measurement, and it doesn't make much logical sense to use an area to describe a length. Lastly, the interquartile range, the difference between Q3 and Q1. This is the only resistant measure of variability that we discuss here, and it is not affected by outliers, or at least not as heavily as the previous three measures. However, by design, it only describes and uses the middle 50% of data. So it does not consider the entire dataset like the standard deviation or the variance does. Furthermore, it also does not give any indication of whether some values are more clustered together, as it cares more about the position of the observations in our dataset and not necessarily their value. If you have any further questions, be sure to review the example videos or ask your instructor.